There's a piece of math running your favorite game that most people quietly gave up on in school. And the game isn't just using it, it's solving it. From scratch, 60 times a second. Miss the deadline by a fraction, and everything hitches. So how does it keep up? This is the line that does most of that work. Position plus velocity times time. Feels like something you do in 3rd grade. But watch. Chop the motion into thin slivers, one for every frame, and lay them under the curve. That's not multiplication anymore. That's an integral stacking up one sliver at a time. And here's what trips people up. Ask around, and folks will swear games are just algebra. But algebra only tells you where a thing is sitting. It can't tell you where it's headed. The second a force shows up, you've got acceleration on your hands. And to get from a force back to a position, you have to integrate twice. So how do you run calculus on a machine that only knows how to take steps? You don't solve the curve. You walk it. One little step. Check what the forces are doing. Step again. Each step is a slice of time called delta time. Nobody can write a tidy formula for 500 crates bouncing down the stairs. So the engine just takes the next step and the next. But there's a catch buried in that. Old games moved things once per frame, so the faster your computer, the faster everything ran. That's why some of those classics are basically unplayable now. Everybody's sprinting. The fix is almost too simple. Just scale every move by how much real time actually passed. Now it plays the same at 30 frames, or 240. Even once you've nailed the timing, there's a deeper problem waiting. Build a simple spring the obvious way, and it won't just wander off. It keeps gaining energy, step after step, until it blows up. That shouldn't happen. So what's going on? Turns out it's updating position with the old velocity. Flip 2 lines so it grabs the new one instead, and everything calms right down. 2 lines. That's the whole difference between rock solid and flying apart. Now you'd figure they'd just grab the most accurate method on the shelf. Nope, the fancy one, RK4, runs the math 4 times every step, costs 4 times as much, and still bleeds energy over time. And at game speed, you honestly can't tell the two apart, so they picked the cheaper, calmer one on purpose. A steady approximation beats a perfect answer that eats your whole frame. Once you know they're cutting corners, you can't stop noticing them. Game gravity is usually 2-3 times stronger than the real thing, because real gravity feels kind of floaty. In a ton of platformers, you dropped faster than you rise, which can't actually happen, and it feels just right. And that rough stone wall, it's flat. Those bumps are faked, painted straight into the lighting. Which leads to the sneakiest trick of the bunch. Send a fast bullet at a thin wall, and it'll go right through. The engine only looks for collisions at each frame. In between, the bullet hops clean past and never lays a finger on it. The fix asks a real calculus question, not did they touch, but when, exactly. And it's pricey enough that most objects never get it. And none of this is some obscure corner case. Unity, Unreal, Godot. Pop the hood, and it's the same thing humming away. A fixed step, feeding a solver, again and again. Here's the kicker. The very first video game, way back in 1958, ran on an analog computer that solved a bouncing ball's motion continuously. The first game anybody ever made was basically a calculus machine. So where's all this going? Some of the new work lets you run the whole thing backward. Instead of asking where the ball lands, you ask what push would drop it right there. The physics turns into something you can solve in reverse. And the latest engines are teaching AI to fake those same equations faster. So next time a world just glides along in front of you, remember, somewhere underneath, an equation's getting solved in the dark, and you never feel a bit of it.